Hello everyone, I'm Xianglin from Fudan University. Today I would like to introduce our latest work, Optimizing Flow Completion Time via Adaptive Buffer Management in Data Center Networks. Nowadays, various applications are deployed in data centers and share the same network infrastructure. Typically, these applications can be categorized into two types: throughput-hungry ones and delay-sensitive ones. The former generate long flows which always try to fill up the buffer to achieve higher link utilization and thus introduce a large queue. Small flows come from delay-sensitive applications and they require small queue at the buffer for low latency. As a result, DCN faces great challenges to enable both high throughput and low latency communications. Well, we can get the three conclusions shown by analyzing representative DCN traffic trace provided from Microsoft. First, most flows in DCNs are short flows, which are less than 1 MB. Second, short flows are transmitted in a high concurrency and high burst manner. Last, the transmission of short flows shows clear on-off pattern. This section shows examples of enqueuing packets from short flows under three different buffer management schemes. In these examples, we assume that long flows are sending 4 packets and consume all the buffer in their corresponding queue during short flows of periods. When short flows tend to be on periods, they send 3 packets in total. The buffer size at the bottleneck switch is 4 packets only. In the case of priority queue, the buffer is split by multiple queues equally. In feature A, since all the buffer is occupied by long flows, all the packets from short flows are dropped, resulting in a timeout for short flows. In feature B, the priority queue, the situation of short flows is a little bit better at the cost of long flows throughput, cause they can only consume half of the buffer. But short flows still have 1 packet dropped. By contrast, in feature C, share the priority queue, since long flows can use all the buffer. All the packets of short flows are dropped as the single queue does, resulting in a timeout for short flows as well. As a result, all 3 buffer management schemes fail to achieve effective buffer management under high concurrency and burstiness DCN traffic. We can conclude above investigations as follows. First, most of the flows in DCN are short flows, which shows high concurrency, high burstiness, and on-off pattern. Second, long flows always try to fill up the buffer to guarantee the high utilization of available bandwidth during short flows of periods, leading to large queuing delay and massive packet drops. Last, the current buffer management can't handle this traffic pattern well due to the FIFO queuing mechanism, resulting in poor performance of short flows. These observations motivate us to find a novel queuing scheme, which can utilize buffer more effectively. In order to achieve efficient buffer management, the solution should not only boost the performance of short flows in their own periods, but also maintain high link utilization for long flows in the off periods. Well, we came up with the scheme called cut-in queue or CQ. When the on-period start, two actions should be performed. Cut in. The packets of short flows are in-queued ahead and switched to avoid massive queuing delay. Injection. The in-queued packets of long flows should back off all jobs to leave switch buffer available for short flows. Recalling from the example above, we demonstrate the advantage of the new scheme using the same settings. When the packets of short flows come to the switch, step 1 and step 2, CQ backs off and drops the packets of long flows. Then step 3, packets from short flows can cut in the hand of the queue, successfully avoiding being jobs and reducing their average queuing delay to 2. Nonetheless, packets from long flows can still utilize all buffer when short flows turn to off periods. But is not directly to achieve the above-mentioned operations, back off and cut in. Therefore, we use multiple priority-based queues to implement less. TSQ and back-off queue. TSQ is transmit queue. At the same time, to prevent the starvation of long flows on periods, we introduce a through K on the TSQ. This feature shows the overall architecture of CQ. Cut-in module, which consists of two functions and two different queues, works after packets finish their routine. It performs different operations in a per-egress port manner according to the type of arriving packets. In details, the incoming packets which are judged as short flow directly go to TSQ if the buffer is not full. Nonetheless, both TSQ and the back-off queue share the same buffer size of their egress ports. In the case of buffer being full, the tail packets in back-off queue will be dropped to make room for the new arriving short flows packet. If the TSQ reach the buffer size, however, the new arriving packets from short flows will be dropped. The incoming packets, which are judged as long flow, directly go to back-off queue and they will be dropped if the buffer is full. In order to achieve efficient cut-in operation in the buffer, CQ leverage two functions called the judging function and the pooling function. Judging function defines which type the incoming packet belongs to. Pooling function decides whether packets in back-off queue should be pushed into TSQ. More details in the paper. In this paper, we implement CQ with DBDK, which is a powerful tool developed by Intel. We use the pipeline model for packet processing. The structure of CQ in DBDK is shown in this picture. Packet processing consists of 3 ports: receiving packets from ingress ports, forwarding packets by proper actions, and delivering packets to the ingress ring buffers. Each part has its dedicated CPU core for its packet processing. In this section, we run several experiments to evaluate the performance of CQ. The testbed consists of CQ prototype switch and 4 hosts. All hosts connect to our CQ switch with 10 Gbps link, making up a small many-to-one topology. In this experiment, we compared the performance of CQ with other 3 different schemes: single queue, priority queue, shared priority queue. Results are shown in features A, B, C, D. When short flows are in on period, single queue has the largest queuing delay. since short flows suffer from the hand of the line blocking brought by long flows. Priority queue and shared priority queue suffer from massive packet jobs due to their inefficient utilization of buffers. In contrast, CQ reduces the queuing delay of short flows by bypassing the in-queued long flows packets, while successfully avoiding most of the packets jobs because it can inject the in-queued packets and utilize the whole buffer, reducing the flow completion time by up to 70% compared with other schemes as shown in Figure C. When short flows are in the off period, long flows can still use the whole buffer to achieve the high throughput in Figure D. This slide shows that CQ can boost the performance of prevent congestion control protocols. In this section, we run a large-scale NS2 simulation to test the performance of different schemes and different network scale. Due to the limited time, here we only introduce our result in lifespan. The FCT of different schemes increasing with the network scale. However, our CQ can still achieve the low-wasted FCT for short flows and higher throughput for long flows. On-off traffic pattern is common in data center networks. Current solutions don't consider this pattern and result in suboptimal performance. We propose a CQ in which the short flow can cut into the hand of long flows packets, resulting in shorter queuing delay, while long flow can still leverage the whole buffer. That's all. Thank you for your listening.